All right, here we go. We're going to try to make this a clear review of our chapter 5 and 6 study guide, where we're really learning about how the distribution of random variables that are discrete or continuous works. So how does the distribution work, and how can we find the mean, calculate probabilities, and generally solve problems. So the intro is almost pointless. Let's get right into the section. So here we go. Oh, I'm supposed to zoom in right here. Well, that should have zoomed in over here. Next time I'll pause before I zoom in. So the very first section was the idea of a discrete random variable. And the best example of this is, for example, menu items or menu items. So what happens when you have a menu is things generally cost a certain amount. So let's say it's a simple sandwich shop. You could have a $7 sandwich, you could have a $10 sandwich, or maybe there's an $11 sandwich, and you choose between those three options. And here you write the probability of getting each one. So maybe the $10 sandwich is the most popular. Maybe that's 60% of the time. And then maybe the $7 sandwich only happens 25% of the time. Well, this would have to add up to 1, or the idea of 100%. That would be 85. This would be 15% of the time. And so there's no formula here like there is with z-scores. But there are some principles. First of all, the sum of the probabilities, P stands for probability, of course, here, must equal 1, which is like the idea of 100%. And when we talk about discrete variables, one thing that's important to realize, these don't have to be whole numbers. There just has to be gaps in between and a certain number of them. So this could be $7.50 for the first sandwich. That's fine. Now, how do you find the mean of these scenarios? That's one of the classic questions. So the mean is like a weighted average. And what that really just means is that means take the first x value, we'll call it x1, which would be 7.5 here, and you times that by its probability. We'll call that p1. That would be 0.25. And you add that with the next one, x2 times p2. And I'm going to run out of room here, but plus dot, 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 plus all the way to the final x value times the final times its final p value, which we would say is xn times pn. And there should be more dots here to show, oh yeah, all the numbers that'd be in between. So that's the mean. What about the standard deviation? Now the standard deviation, first, also, we can write the mean in a more slick way. We could say the mean, mu, equals the sum, which this stands for sum, the capital sigma, of the xi's times the pi's. And I stands for, it's the index, and it's just a fancy way of a placeholder for 1 to 2 to however many there are. And that's the mean. It's the sum of the products of x values times the probabilities. Now, the standard deviation formula is similar in the sense that it is multiplied out, but it is the sum, and what you sum is you subtract each x value from the mean. So that would actually be this entire calculation, which you sometimes have to do first. And you subtract each x value from the mean, and you square it, and you 10 times it by its probability. And then you sum up all those results. And this should be a pi, and xi, and a pi, because I wrote it in sigma notation. You don't do z-scores. But while we're here, let's fill this in. What do z-scores represent? Z-scores in general, which happens at the end of chapter 5 a lot and chapter 6, is really what it is it's a count of the number of standard deviations x value or any value is from the mean. So it represents the number of standard deviations from the mean. And so if you have a x value or some individual has a z-score of 4, well, that's a very large value because there are 4 standard deviations above the mean. Each standard deviation has a certain size, a certain value. And so if you're 4 standard deviations above the mean, you're quite high. Okay. That was the first 2 sections. Now, in the next 2 sections, 5.3 and 5.4, what's really going on? We have binomial random variables. That's basically a particular type of discrete random variable. And what you're really doing, hey, you could make a table, right? What would the table be? The table would be x could be 1, or I should say 0, 1, 2, 3, because what you're really doing here is x is just a count. It's a count of something, and it's a count when there's a probability of a thing happening or not happening, and we call that success or failure. And so these are the classic scenarios where you have a certain number of trials, and then we're looking for a certain number of successes from those trials. And it doesn't have to be a success, but a certain number of things where it's like, basically each trial is either A or B, yes or no, true or false, category 1 or category 2. And we're looking for the number of times the first or the second one of those categories occurs. And n is always larger than k. I mean, I guess they could be equal, right? But at k cannot be larger than n. And so what's the strategy? How do you find probabilities when this is happening? Now, be careful. There's really 2 probabilities. P is the probability of success. And that's very important to understand that that's different than when if you say this, the probability of x equaling 4, that's the probability of getting 4 successful events out of your number of trials. P, the probability of success, stays the same the whole time. And so what's the formula here? Well, first, we don't usually say x equals 4 all the time. We'd say, in general, that's where the k is. So whatever number is there, that should be your k. And this formula I know we've seen many times. And you can really easily plug this formula into Desmos. And just as a quick review, P, chance of success. K, the number of successes. Because each one of these probabilities has to happen a certain number of times. Well, however many times you're going for the success. And then Q is the chance of failure, and n minus Q is the number of failures because it's the number of leftovers from when you take away the number of successes. And the job that this thing is doing, the NCK, the combination, is it's counting up the number of ways that this could occur. Because if you want to calculate the probability of getting a certain number of successes, those could happen in any order within the n tries. And if NCK, if that is too large, then you can't, if NCK is not too large, you can use Desmos. But if it's very large, then you can use an online calculator such as StatTrak. Now, in chapter 6, we learn a way to approximate this, so kind of a way to get around NCK. But if you want to get the exact answer, you would need an online calculator, as this formula kind of falls apart when, it doesn't fall apart, but it just becomes impossible to calculate. Now, the mean here, one thing that's really important to understand is that really when we talk about mean, really mean is essentially the expected value. It's the expected value. And it's important to understand that because having that context just helps things make sense. So what's the mean? Well, how many x's would we expect to be successful out of n trials? Well, the number we would expect, mu, the mean, would be just, well, it would be the probability of success times the number of trials. Because if that's like 30% and you're doing something 50 times, so it would go, 0.3 times 50. So it's the number of trials, and that would be that'd be, if you expect every single one, but no, you times it by P, the chance of success, because that brings you down. It's basically taking the percentage of the total that you want, that you would expect. And so that's the mean, perhaps a long explanation. Now the standard deviation is an interesting formula, and it's lowercase sigma for standard deviation. It's the square root of n times p times q, which is easy to calculate on a calculator. The trick here is to realize, I need this formula. When do you need it? You need it in these scenarios. So once you're doing it, you usually calculate it correctly. The tricky thing is knowing when to pull it out of your pocket. And there's no z-scores here again because it's difficult to explain why, but essentially, z-scores are used for a normal distribution. And while we learn later that the bar chart for when x is 1, when x is 2, when x is 3, it is generally normal when you have a large enough n. It's still not exactly normal, and so we don't really use z-scores with these. When we're calculating this, we don't use z-scores. Okay, pause. Something else to bear in mind here, just for a quick second, is when you have the probability that x is less than k, let's say x is less than 3, less than or equal to 3, it's a typical type of problem. How would you do that? Well, you would have to do the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2, because you don't care whether it's 3 or lower, so it could be any of these, plus also the probability that x could be 3. And each one of these, this and this and this and this, each one of those requires its own calculation. And so that's important to bear in mind. Let's do continuous. Now, the binomial random variable is an example of a discrete variable, and it's the most classic, essential example where you have a count and a probability of success for each trial. Now, continuous random variables is very different, very different. We're not looking at a count of individuals. What we're doing is we have a population of individuals, and we're measuring something about them. It could be a height, it could be a weight, it could be a whole bunch of different phone chargers, and we're looking at the wattage, right? And what's the amount of wattage from each phone charger? So something that we can measure and that's continuous. Height, weight, excellent examples, because length, because they're so simple. Problems we study, the distribution of a continuous variable for all the individuals is usually normal. When that happens, we use our standard normal table. That table that we've looked at so many times, that has z-scores on the side and then has the probabilities in the center. Let's read this, which essentially has all the decimal values for blank from 0 to 1. Well, what are all those values? You could say percentiles, you could say probabilities, you could say, in a sense, percentages. I'm going to say probabilities. And so has all the probabilities from 0 to 1 inside the middle of that chart. And really understand each x is the measured value for an individual, so the length of each individual. Now, if you're looking for the probability of x being larger than a value, so let's say we're looking at the probability that x is larger, a certain little insect is larger than 2.1 centimeters. If that's the case, the trick here, when you're using the z-score table, is really the first thing you have to do is you have to rewrite this as x less than. And the trick for that is to subtract from 1. So the probability of x being greater than a value is immediately equal to 1 minus the probability of x being less than a value. And the reason why that works is, all the problems we're doing are essentially normal, right? And what that means is the distribution has this shape. And so if this is a certain x value, like 2.1, and we want to know the probability of being larger than 2.1, so that would be the probability being over here, right? That's this right here. If we want to know that, there's no way to look this up. Well, there's an easy way. What you do is you look up this red area, And how do you get the green area from the red area? Well, the total area is 1. The total area is 1. So if you want the green area, which is what's being asked for a lot of the time, you find the red area on the z-score table, and the red area is the probability of x being less than a value. So this red area is from the z-score table, also known as the standard normal table. These curves are called density curves, and let's leave it at that for the moment. Now, what's the mean? The mean is all the individuals in the population added up, divided by how many there are. The easy way to write that is this way. Now, most of the time, this is given to you, right? They're giving you the mean of the population. But it's very interesting. Remember this if you ever really need to find it or calculate it for some reason. This is very helpful to remember. Oh, it's just the mean, right? With the mean weight would just mean length would be add up all the individuals divided by n. Now, in a similar spirit, this next box right here, standard deviation, very interesting. Standard deviation is something, we learned this formula way back in chapter 1 or 2. But standard deviation is, well, what is it? It is the difference of each individual from the mean, and then that gets squared and summed up. Then you divide that by n. And so really what you're doing is you're finding the average distance from the mean. Well, really it's the square of the typical distance from the mean, and then you divide by n because you summed it up that many times. And the last thing is that because there was a square, you would do a square root over the whole thing to kind of counterbalance that. Now, this is the standard deviation of a population. If you're talking about the standard deviation of a sample, we'll use S. And this is sort of a particular rule that is important, especially in AP Stats. In our class, we haven't focused on it a million times, but it's the same formula, except of course, this is the sample mean, and you divide by n minus 1. And there's many videos on YouTube that go into long explanations about why this happens. The beautiful thing is that most of the time, all this stuff right here, the mean and the standard deviation, is given to you. And to be honest, if one of these is not given to you, they're not expecting you to do this. Why are they not expecting you to do this? Well, because you have to know every single individual in the population, right? Each individual minus the mean squared. That's like impossible, right? So most of the time when there's information that's missing in one of these problems, what you're going to do is you're going to use the z-score formula. And you're going to use z equals x minus the mean divided by the standard deviation. And a lot of the time it's like you can find the z-score from the table by looking at by being given a probability, and then you can find the z-score, and then you might know the mean, you might know a particular x value, so you'll have something like this. Let's say we know this: the probability that x is less than, I don't know, 4.8 centimeters. Let's say we're talking about some little insect again. Let's say that probability is 37%. Well, that's a little gold mine of information, because what happens is that this probability allows us to find what is the z-score for 4.8. So you would look up this probability in the middle of the table, and you would see the z-score associated with it. So you would essentially find what you'd be finding. You say that means z is less than probability of z being less than some number equals 0.37, and you would find that number on the table, and that's the number that is associated with 4.8 as an x value. And why that's so helpful? Okay, so what's given to you one more time? Probability that x is less than 4.8. It's given to you that that's a 37% chance. When they give you that, they're essentially giving you the z-score. because you would go on the table, look up 0.37 in the middle of the table, and find the z-score. Once you find that z value, you can then come back up here and set it up. So this number right here would go right here. Number equals 4.8 minus the mean that's given to you. And then let's say you're trying to solve for the standard. Let's say you're trying to solve for the standard deviation. I'll put that in purple. You would, well, you could put a 1 on the bottom and cross multiply. You could multiply both sides by sigma and then divide by this number. And so it's very important to realize that this is really at the heart of the algebraic work. Repetitive advice right here, very repetitive advice. It's so important that you practice this, and if you're not understanding, you ask your instructor. For most of you, I'm your instructor. Ask questions. You know, I understand the no asking questions thing. I get it. There's many reasons. You just need to get over all of them and make it happen. You'll appreciate yourself for doing it. Now, in Chapter 6, we're continuing and expanding on all the ideas from Chapter 5. What's going on? Now, 6.1 and 6.2 was vocabulary. 6.3 is where you really learn a technique. And it's back to binomial random variables. But the difference is that basically what's going on is that if you have, let's say a typical, let's say n equals 6, and if when you have a typical, like let's say this is the chance that your number of successes is 0, you could have, that could happen like 10% of the time. And this is back to success or failure. You could have a few more chances where they're 1, right? X equals 2. Maybe that's the most popular for whatever reason. X equals 3, 4, 5. Now this is not a good example because it's not a very big table, but X could be 0, 1, 2, 3, 4, 5, or 6. And get all 6 correct, right? But the idea here is that this is basically a normal curve. And because this is a normal curve, you can treat it like a normal distribution approximately to get approximate answers and use z-scores and all that stuff. So what's the main technique? Approximate a discrete binomial count, which is the 5.4 stuff or whatever it is, right? What was that? That was 5.4, right? Sorry. Microsoft Word is so frustrating sometimes. You know, I could write them such a good letter. Anyway, I had to delete this, but what we were talking about was that a binomial distribution, when you make a chart of the results, x could be 1 or 2, 0, 1 or 2 up to 6, whatever, it's basically normal. Basically a normal distribution, that bell-shaped curve. And so you can approximate a discrete binomial scenario count. You can approximate the probability of that count by using a normal curve because the binomial distribution is approximately normal. Now you can do these problems two ways. You can approximate the count or you can approximate the proportion. And it's really the same thing. And you can do it also because the distribution is approximately normal. Now let's discuss both ways. First, as a count. So when you do these problems as a count, you know what you need is you need the z-score. And I'll try to keep this color-coded. Let's do this in purple. So as purple right here. What's the mean? Well, let's start actually with the z-score. So how does the z-score work when you're doing it as a count? As a count, the mean is going to be, and I should zoom in right here now that we got as a count, the z-score is, well, it's a count. So you're looking for a certain x value, and you're going to subtract from the mean that you would expect, and you would divide by the standard deviation. And we're dividing by the standard deviation of x, if you want to put a subscript to talk about what we're doing. And so the count would be that the mean count that we would expect would be, well, back to good old n times p, because that's the mean number that we would expect. This is the number expected. You could call this the count expected, or the expected count. What is the standard deviation? Well, that's the good old standard deviation of n times p times q, because that's the standard deviation of the count. And you use this z-score with this standard deviation and this mean to approximate a binomial scenario. Now, the one thing to bear in mind is that there's that whole idea of continuity adjustment. So the technique involved is that, let's say if we're looking for the chance that x is less than or equal to 7. Well, when we approximate that, we want it to be the probability that x is less than 7.5, because those decimals that are lower than 7.5 would round to 7. Another example of that would be, let's say the probability that x is less than 100. Now here, 100 is not included because it's strictly less than and not, there's no equal to. So because of that, we don't want to include 100. So when we do this, we would actually calculate using 99.5. Now, if you look up continuity correction in Google, you'll see charts that show you this, and they'll show you with all the different scenarios. Oh, if it's greater than, how do you do the 0.5? It's best if you can not necessarily like rely on looking up the Google image or looking at your notes, but that you understand it instinctively, that you're trying to capture the whole number. So you need to either expand or shrink the 0.5 to be more inclusive or less inclusive, depending on what is called for. Okay, that's when you're doing it as a count. So actually, move this over here, because those are when it's a count. This is called this is continuity correction. Okay, I should be pausing more. Sorry, I'm just going. Who cares? Has this been this long already? Oh my goodness. Continuing and finishing. What if you want to do this as a proportion? Now, it's the same way. Let's jump back to our z-score. How do you write the z-score as a proportion? I'll do this one in magenta. So when it's a proportion, what you're doing is you're looking for a certain proportion, a percentage to come out. So instead of it being an x value, it's a percentage, and that's going to be minus, now what you would compare it with, instead of taking x minus the expected number of the count, it'd actually be, you'd compare it with the percentage from the population. So p is from the population. And we would divide that by the standard deviation of proportions. So what proportion would you expect? Well, you would expect p. What's the standard deviation of the proportion? Well, it's really this, but you divide by n essentially, because you're looking for a proportion. So the standard deviation of proportions is the square root of p times q divided by n, and the square root. So how does this look in practice? Let's get right to it. Let's say that we have a number of trials is 50, and we're going for something simple like 30 successes. And let's say the chance of success is 0.8. So the chance of failure would be 0.2. So it'd be pretty easy here. Okay, n and p, plug it in. N and p, plug it in, right? But what about the proportion? I think this is good to see. So here, what we would expect, the expected mean would be 0.8, because we would just expect the proportion, right? And this would, you just calculate this, and that would be whatever the square root of 0.8 times 0.2 divided by 50 is, and that's the standard deviation. And then when you come over here, well, you would say, this is good. See, I bet you're not sure what's happening. Well, this value would go down here, right? So this value would just go down there into the standard deviation. And of course, this would be minus the 0.8, the proportion we would expect. But what the heck goes here? What the heck goes here? The proportion that we would expect, p hat, or not that we would expect. P is what we expect. P hat is what we're going for. We're going for 30. So what would that proportion be? Well, in that case, that would be, you would say that's 30 divided by 50, which is 0.6. And we would then put 0.6 right here, and the standard deviation on the bottom. And what would this be calculating? This would be calculating the probability that x is less than or equal to 30. So if that's asked and you want to do it as a proportion, you can convert it this way. You could also just do it in the purple, right, and just keep it as a count of 30. By the way, I hope you all realize that once you find the z-score, that you then go to the standard normal table and look up the probability. Also, if you were going to do this as a count, you should put a 0.5 here to include it, the count, to include the 30 completely. All right, and now the final thing we learned about is the sample mean. The sample mean. The sample mean. The sample mean. What is the sample mean? What that's talking about is that instead of looking like in 5.7, instead of talking about the distribution of individuals, it's still based on the distribution of individuals, but we're talking about you grab a group of those individuals, and we call that group a sample. So what's the technique used? What's cool about this is that the original population, if it's normal, you're good. And even if the original population is not normal, so if the original population distribution is normal, or if the sample size is roughly 30 or more, so you don't have to even have a normal population. All you need is 30 or more in your sample, and then the distribution of the sample means are normal. And the sample means are all x bar. That's a sample mean. That's a sample mean. So you grab 30 individuals, you take their average, that average is x bar. You can do that many times. You take many samples. And the distribution of all the x bars is going to be normal. If the original population is not normal, and or the sample size is too small, so that means you have less than 30, then the distribution of sample means is not normal. And that only happens occasionally. You know, that's like the typical like multiple choice problem. Why is this problem not valid? Oh, because you didn't have 30 in your sample and because the population originally was not normal. That's why you couldn't do it. But most of the time, you're going to have either a normal population or 30 in your group, in your sample. And yeah, so how does this work? Well, you're going to use z-scores. So what's the z going to be? The z is going to be the value you were going for. So let's say the typical problem is, what's the probability that a sample mean is less than 5.8? That means the mean of your group comes out to be less than or equal to 5.8. So you would use a z-score, and the sample means are normally distributed, so that's why you can do it. And it'd be x minus the mean. Now, what are we talking about? Well, we're talking about the mean of sample means. And we'll be dividing by the standard deviation of sample means. So those are actually easy. The mean of sample means is actually just the mean of the population. It has to be, because the mean of all the samples has to line up with where the mean of the population is. So that's really nice. And then the standard deviation just needs a slick formula. The standard deviation of sample means, well, it's really the standard deviation of the population. But when you ask more individuals, the variability starts to decrease. And when variability decreases, well, standard deviation is measuring variability. And the way that this formula works is it reduces the variability as n gets larger. Because as your sample size increases, you're going to be closer to the mean. There's less chances for randomness. There's a law of averages that kicks in. And so the standard deviation that you're going to be using is the normal standard deviation from the population divided by the square root of n. And you would calculate that, and whatever this value is, that would go under the z-score. And then you would use z-scores normally to answer a problem like this. Yeah, the mean of the sample means is actually the mean of the population. And the standard deviation of sample means is the difference between the typical sample mean and the population mean. Yeah. How far off is your sample mean from the population mean? That's standard deviation of the sample means. That's this value. So I don't know how helpful this was. I hope it was. I should link this document in the description. All right. Have a good one. Good luck. Hey, ask me questions, please.